That was super exciting. All right, section 11.1, we're going to talk about empirical and theoretical probability. So the first thing that relates to the idea of empirical probability is we look at what's called an experiment. Okay, and in an experiment, that is a controlled operation that is going to yield a set of results. Okay, so it's the results that we are going to look at for our probability. The set of all possible results of an experiment is called its outcomes. So just getting you used to some of the words that you're going to see very frequently as we go through this unit in chapter 11. And then out of all of the possible outcomes, what we will consider is some event. An event is a subset of all of the outcomes of an experiment. So for instance, just so that you can understand the verbiage that I have just presented to you, we're going to consider the experiment, okay, of rolling a die. Okay. Die is the singular of dice. Okay, so if you like to play Monopoly or Yahtzee or whatever the dice games are, okay, if you just have one, that is a die. So we're going to consider just one standard die. We're not playing Dungeons and Dragons, so we don't have any tetrahedrons or anything like that. So when I roll a die, okay, the experiment is rolling it. I can look at the outcomes. So the outcomes, remember, are just every possible thing that can happen. So what's every possible thing that can happen when I roll a die? Sure, 1 through 6. So 1, 2, 3, 4, 5, 6. Okay. Those are the possible outcomes. Now we can talk about events, and I'm just going to make up a couple of events here, and these are the things that we can find a probability of. So some different events might be rolling a 2. Okay, that is an event that I can calculate the probability of. Another event would be rolling an even number. Again, each of these events is some subset of these possible outcomes. So if I'm rolling an even number, what outcomes am I looking at there? Perfect, 2, 4, 6. And then one more, if I'm going to look at rolling a number greater than 2. And what outcomes is that taken into account, that event of rolling a number greater than 2? 3, 4, 5, 6, perfection. Okay, if you can identify the different outcomes and then the subsets, you are halfway to being able to calculate probability. So there are 2 types of probability that we're going to talk about. When we boil it all down, they're calculated in the same way, okay, but they're just based on different things. The first one is called empirical probability. Am I going too fast? Everybody caught up with me? Let me know. I get excited. Wave your hand. Empirical probability. So empirical probability is determined through the actual results of an experiment. So what you have is it's the probability of an event the next time the experiment is performed. So empirical probability, you're actually looking at data. Okay? You're not necessarily looking at what should happen in theory. We're going to talk about that. That's the other type of probability called theoretical probability. We'll talk about that in a minute. But for empirical probability, we are just looking at the actual results. And so the way you calculate it, our empirical probability of an event, the notation goes like this. We're going to use a capital P in this class for probability. Other books might use a lowercase p. So if you bump into probability in another class situation, you might see that. But our book uses capital P. And then inside the parentheses, you'll write whatever the event is. I've just used an E for the word event. Okay, so the probability of event is going to be this. The number of times the event occurs divided by the total number of times the experiment was performed. So to calculate the probability, you look at the number of times the event that you've described happens divided by the total number of times you did the experiment. Or another way to say it is it's the successes divided by the total. Okay, so it's the successes divided by the total. So here's my first example of a probability problem, empirical probability. So in this example, it says I've tossed a coin 100 times. By the way, the word fair in probability and statistics, when you see that, when math people use the word fair, it's not the morality of fair. Fair just means equally likely. Okay, so that's what's happening here. So equally likely. So when you see that word, the fair coin means that the chances of it landing with the heads up or the other side, the tails up, is going to be the same. And the probability that we deal with in this unit, I think everything, but I don't want to be wrong here. Everything is equally likely outcomes. Okay, we're not going to deal with anything in this class where the chance of one thing happening is weighted in some respect. So that would be a little bit of a deeper dive into probability. So in 100 tosses of a fair coin, 44 landed heads up. So what's the empirical probability? Again, the empirical, so we are looking at the results of this experiment right here. Okay, the data that I'm given. So what's the empirical probability of the coin landing heads up? All right, so here's my capital P for probability. Inside the parentheses, I'm going to write the word heads because that's the event that I'm concerned about. Probability is successes divided by total. How many times did I successfully get this according to the experiment? 44. Out of how many total times was the experiment performed? 100. As far as probability, you have two options in my class. Whenever you're doing a My Math Lab problem, make sure you're just following their instructions, how they want things. But I like two things. Either if you're going to use a fraction, if you're going to leave it as a fraction, make sure it's reduced. Okay, so I'm going to reduce the fraction. 4 goes into both 44 and 100. 4 goes into 44 11 times. 4 goes into 125 times. So this is my reduced fraction. It's my reduced ratio. This means that I have 11 successes for every 25 times I flip this coin. Or the other thing you might want to do is just use your calculator and make a decimal. And if you round, I like it to be rounded to the 4th decimal place. Okay, it gives us enough significant figures to be able to be interested, but not too many that you're writing all day. My Math Lab might ask for 3. A lot of books just like 3 decimal places. I like 4 just to get that little bit of extra accuracy. This, when I take 11 and divide it by 25, it's 0.44. So it terminates, so it only goes to the 2nd decimal place. So remember, empirical probability, what this is telling me is, according to this experiment, the next time I flip the coin, there's a 44% chance, or 44 out of 100 chance, that the next time is going to be heads up. Okay, that's the result of the experiment. You tracking with me so far? All right, well, exercise 1. Okay, you are standing outside the Virgin Music store in Times Square. 60 people went into the store and you selected them at random and were asked to choose, you asked them to choose their favorite type of music. And so here is the data that you got from doing this experiment. You found out that 60 out of the 60, 12 chose rock music, 16 like hip hop, 8 chose country, and 24 chose some other category of music. Determine the empirical probability of each of those 3 things, please. All right, so for the first one, probability that the person likes rock. So again, we're looking at what's the probability that the next person I go up to and say, well, what's your favorite type of music, is going to give these according to the data that I have. So how many people agreed with rock music? 12 out of how many total times was this experiment done? Perfect, 12 out of 60. Now, if you chose to reduce this, 12 goes into both of those, 12 goes into 12 once, 12 goes into 65 times. Or if you chose to make a decimal, 12 divided by 60 is 0.2. By the way, you do not have to do both of those things. I'm just doing both for these first few examples just to show you the options. You only need to pick one way to write the answer, okay? Just in case you're wondering. So for the next one, hip hop, what's the numerator? What's the number of successes for this one? 16 out of, perfect, 16 out of 64 goes into both of those if you chose to reduce. 4 goes into 16 4 times, 4 goes into 60 15 times. And when you go ahead and do that in your calculator, somebody's got it. My phone's not behaving. Oh, there we go. Now it's behaving. Here we go. I've got 16 divided by 60. You got 0.266666 forever. So I'm going to round that to the fourth decimal place. So that's 0.2667 is the decimal. And then last but not least, my other, how many people liked something else? That is true, 24 out of the 60. Again, if you chose to reduce, 12 goes into both of those, 2 out of 5, or if you made a decimal out of it, you're looking at the decimal 0.4. How'd you do? We doing okay? Any feedback for me? Are we doing okay? I want you to. So we're going to turn the page. Exercise 2. It's another empirical probability problem. We're looking at the results of some sort of pharmaceutical test. So go ahead and calculate the probabilities. All right, so just according to the data that we have here, how many people experienced reduced blood pressure? 379 out of 500 people that were given this drug. And so when I pop that into my calculator, 379 divided by 500, I'm not going to bother trying to reduce. That's 0.758. The next one, how many people experience unchanged? Yep, that is great. 62 out of that 500, and 62 divided by 500 is going to give you 0.124. And then last but not least, the number of people that it did not work for and actually got increased blood pressure is 59 out of 500. And that turns out to be 0.118. Are we all agreeing on the numbers? We doing good still? Okay, so that's it. That's empirical probability based on an experiment. So before we get to theoretical probability, we need to talk about what's called the law of large numbers. And what this says is, the law of large numbers says is, it states that the probability statements apply to a large number of trials of an experiment. Additionally, as the number of trials increases, the empirical probability from our experiment approaches what's called the theoretical probability, which is where we're going to turn our attention in just a minute. So what the law of large numbers says is this. Again, just to use sports, since that's something concrete. At the beginning of, let's say, the basketball season, if you're fond of basketball, you go to the free throw line and you shoot and you make your first free throw. You are now 1 out of 1, right? 1 divided by 1 is 1. You now have 100% probability of making free throws. Does that mean that for the rest of the season, you are now going to make every free throw? No. Okay. Your free throw percentage is going to come into further view as the season goes on and you shoot more and more and more free throws. Then you're going to get a clearer picture of if you are a good free throw shooter or if you are a poor free throw shooter. It's the law of large numbers in action. Okay. And so this is just a chart I got out of the book that expresses the same sort of thing. It's about tossing a coin and looking at the number of heads that we get. And I'm hoping that they didn't make a student sit around and do this, that they had a computer do it. But so we notice we flip the coin 10 times. You would expect, since a coin has 2 sides, you'd expect half of it in theory, you'd expect 5 of the trials to end up heads, but we got 4. But notice we only missed by 1. Okay, it's only 1 different than what you'd expect. But here's the issue. Since you only did the experiment 10 times, each of those 1 is a significant amount, a significant portion of the 10. So your probability, empirical probability of getting a heads is 0.4. That seems to be pretty significantly different than 0.5. Now notice in the second line, now we've done the experiment 100 times. Okay, we've increased by a factor of 10. Again, we would expect 50 heads. But this time we got 45. But notice here, we're 5 different than we would expect. We've got 5 fewer heads than we would expect. But here's the thing. Because I've done the experiment 100 times, each of those individuals matters less. Okay, so they're less significant. And so the empirical probability is 0.45. So notice I get a little closer to what I would expect. Now, I'm not going to bore you, go through every line of this. I'm just going to skip down to the bottom. Okay, so we forced some student to flip a coin 100,000 times. We took their whole spring break to do it. We would expect 50,000 of those to be heads because there's only 2 possible outcomes. But this time we got 49,770. So we're still below what we'd expect. In fact, we're 230 below. But again, due to the law of large numbers, and this is why you do things a lot of times, since we did this 100,000 times, each of those individual ones is very, very insignificant. And so that's why you can see that the empirical probability is getting really, really close to 0.5. So that's why when they are, to relate this to when they were doing the COVID vaccine trials, right, they would get a large group of people because they want to see what are the side effects. Does this thing actually work or anything? So you wouldn't just give it to 1 or 2 people because you can't tell anything from that. So you take advantage of the law of large numbers. Now, if you take a statistics class, which I highly recommend, if you need another math credit and you don't know what to take, statistics is really great. If you're going to be a teacher or anything like that, you'll probably have to take statistics for teachers at some point in your junior or senior year, because it's related to testing and outcomes and things like that. But statistics is a great thing. You'll learn about how you pick an appropriate sample size, like how big is enough to be able to make a good determination. So that's something that you learn. Anyway, all that to say, the law of large numbers. You don't just judge probability based on one or two trials. So flipping the page now, we talked about empirical probability, which is looking at the results. The other type of probability that we're going to turn our attention to is called theoretical probability. And so the blanks here, these are going to be a letdown. The theoretical probability, you're just rewriting. But I feel like I've got to make you write something. The theoretical probability is calculated by considering all of the equally likely outcomes. Again, we're only going to deal with situations where things are equally likely. We're not going to deal with weighted probabilities. That would be a whole another level of complexity. So the theoretical probability of an event, again, the notation's the same. The probability of an event is the number of outcomes in your event E divided by the total number of outcomes. And again, this boils down to being the same thing. The number of outcomes in E. So that is successes. How many successes are there? How many outcomes do you care about? Divided by total. So whether it's empirical or whether it's theoretical, it is the same ratio. It's successes divided by total. Okay, if you just keep that in mind, that's how you're going to calculate probability. So here's my example. Then I've just got a bunch of examples for you, so you see the different situations that you're going to encounter in your homework. A fair die is rolled. We already saw that event on the first page. The outcomes are 1 through 6. We're going to calculate the probability of these various things together. So the first thing is the probability that I roll a 2. So if you need to, you can flip back to the front page. You can look at the number of outcomes there are. So what's the probability I roll a 2? Well, how many successes are there? 1. There's only 1 2 on the sides of my die. So 1 out of how many total number of outcomes? 6. There you go. You're done. If you don't want to deal with anything else, that is a reduced fraction. But if you are a lover of decimals, then you could also write 0.1667. Okay, I like the 4th decimal place. I think my math lab likes the 3rd. So just make sure you're following their instructions. The next one, the probability of an even. Okay. Well, how many successes do I have here? 3. There's the 2, the 4, the 6. Those are the even numbers on the die out of, again, my 6 outcomes. And so 3 out of 6 reduces to 1/2, or the decimal 0.5 if you prefer that. We doing good? All right, well then the number greater than 2, I'm going to use the math symbol for greater just because I'm lazy. The probability that I roll a number greater than 2. So how many successes does that represent? There are 4 successful outcomes, the 3, the 4, the 5, the 6. By the way, don't assume greater than or equal to. This just says greater than. Okay, so if I wanted greater than or equal to, I would say greater than or equal to. So there's 4 possible successes out of 6, which reduces to 2/3. Or if you pop that into your calculator, that is 0.6667. Okay. On my die, what's the probability I roll a 7? How many 7s are there? You all are identifying that very well. There are 0 7s on my die out of 6. So 0 out of 6. So the reason I put that on there is just to highlight this. When you get a probability of 0, that is an impossible event. That's something that won't happen or can't happen. So that gives you the lower boundary of probability values. You're never going to have a probability less than 0. Okay, you can't have a lower probability than that. How about this one? What's the probability of a number less than 7? How many of my outcomes have a less than 7? 6 out of 6. So that's 1 or 100%. And again, the reason I put that on there, that is a certainty. Okay, so an event that's certain to happen. The probability equals 1. So this tells us something about probability. So the probability of any event, E is always going to fall into this range of values. Okay, you will never, if you've done it properly, get a probability outside of this. The probability is always going to be bigger than or equal to 0. And it's always going to be less than or equal to 1. And the larger the decimal is, the more likely it is to happen. So forget the D and the E. Of the A, the B, and the C, which one of those 3 things is the most likely to happen? C, forget D and E. Sorry about that if you didn't hear it. Forget D and E. Of the A, B, and C, which one's most likely? C, because it's 0.667. That is the largest one. And the one that's least likely to happen is A. It's 0.166. The lower the number, the less likely something's to happen. And generally, people that deal with probability, they would consider something like 0.005. If a probability is 0.005, then that's called an unlikely event. That's just kind of the terminology that I'm not going to quiz you on that, but just letting you know. Okay, so that gives us our range of values, and when we see probabilities closer to 1, that means they're more likely to happen. All right, here's your next one. Again, we're just doing theoretical probability. Exercise 3, you're at a picnic, and you know that in the cooler there's 100 ice cream cups, because ice cream's awesome. They are all the same size. There are 40 vanilla, 20 mint, 30 strawberry, 10 chocolate cups. If you reach your hand into the cooler, and you're going to select one at random, determine the probability of each of those 3 events, please. All right, so when I consider this at random, what's the probability of strawberry? How many strawberry cups are there? Out of 100, perfect. And so that's going to be 0.3 when you make a decimal out of that, or 3 out of 10 if you reduced the fraction. How about vanilla or chocolate? How many vanilla or chocolate cups are there? Okay, there are 40 vanilla and there's 10 chocolate. So that adds up to a grand total of 50 successes in that event out of the 100. So that's 5 out of 10 or 1 out of 2, 0.5. So half the time you're going to get one of those 2. If you think mint ice cream is gross like I do, you're concerned with the probability that you don't get a mint cup. So how many not mint cups are there? 80. Yep, 80 out of 100. Great. And that is going to be 0.8. We still doing okay with our theoretical probability. Remember, if you have any question, please raise your hand. I'm just going to keep rolling forward. You're not an interruption or a bother if you have a question. So exercise 4, the reason I put these next few exercises on is because reading a table is going to come up at a couple different points in our unit, and I just want to make sure you can find the values that we need. So at the bottom of the page, just do the A problem. We'll go one at a time. According to this, we've got these vehicles on the lot. If we're just picking a vehicle at random, because I guess that's how you buy your vehicle, what's the probability here you're going to buy a car? So go ahead and calculate the probability that you buy a car. According to this table, how many cars are there? Okay, 85. This number right here, we didn't make any specificity, so we didn't ask anything about the brand. We just wanted to know the car. There are 85 cars out of how many total vehicles? Okay, so out of 200 vehicles, you're welcome to reduce that if you want, but I'm just going to use my calculator, and that's 0.425. So far, are we so good? All right, then flip the page. There are 4 more problems based on that table. So if you would go ahead and do each of those 4, and we'll check in with each other in just a minute. All right, so going through this, the next one, the probability of an SUV. How many SUVs do I have on the table? Yeah, right here, this number right here, 45. And so that's 45 out of the total of 200. And when I do that in the calculator, 45 divided by 200 is 0.225. Any questions, comments, concerns? Yeah, please let me know. Toyota, what's the probability I pick a Toyota? How many Toyotas are there? 77. Yep, there are 77 of those. Okay, again, I'm just making sure you can read the table. So 77 divided by 200 turns out to be 0.385. How about GM trucks? So I'm getting a little more specific. How many of those are there? Yep, there are 40 right there. So 40 out of 200. And so 40 out of 200 is going to reduce to 0.2. And then last but not least, how many not cars are there in this? Yeah, there's 85, so I could subtract that, or I could just add up the other things. Either way, you end up with 115 out of the 200, and 115 divided by 200 is 0.575. All right, just a few more examples of different things. So we're approaching the finish line today. So again, if you've got any questions, like I said at the top of our class time together, I'm only doing this one section because I want you to be perfect at it, please. So do as much practice as you possibly can. All right, so decks of cards are used a lot in probability because there's enough options to keep the problems interesting, but it's not too large of a thing where the numbers are super bulky. So I do not assume that you are a card player or know anything about cards. So I will give you this picture of the deck of cards if I put card problems on the test. So you no need to feel intimidated, but just some attributes of the deck of cards. All together, there are 52 cards. So if you count up all of the images there are 52 cards in the deck of cards. And you can see from the picture that I've given you, they are divided up into a couple different ways. The first thing, they're divided up by color. So you've got black cards and red cards. Okay, so just help me out with this basic arithmetic. If I've got 52 cards and I've got two different colors, how many of each are there? Yeah, there's 26. 52 divided by 2 is 26. There's 26 black cards, 26 red cards. They are further divided up by what's called suits, and those are the different shapes. I can never remember which one's which. I think this one's the club. I can't spell it. Okay, these are clubs, the ones that look like a clover. And then the next one are called spades. And then we've got hearts, and then finally diamonds. Okay, and those are the different suits that the cards are divided up. There's 2 black suits, there's 2 red suits as far as our deck of cards. So again, just helping me out so you know these basic facts. If there are 26 black cards and the black cards are divided into 2 suits, how many of each suit are there? There's 13. Okay, it's all symmetric. That's one of the nice things about the deck of cards and why it's used for probability. The last 2 things, real quick, if you are a card player, just so you know, we are going to count the aces 1 just to keep things simple. Okay, so if you're asked for a problem about cards less than 4 or something like that, the ace is just 1. Okay, it's not a high card, it's not going to be a random card. And then also the jack, the queen, the king, these cards right here. Some books or some people will call these the picture cards. I think that's what our book uses. Some people call them the face cards because they all seem to have faces. Okay, so that's all I need you to know about a deck of cards. But again, if you don't know that, I will give you this same chart on the test. So don't stress about that. But now, given that drawing right there, what I would like you to do, please, is there are 6 questions in exercise 5 based on the deck of cards. If you could go ahead and do those. right, so I'm going to get started. If you're still working, keep working. If you got any questions, let me know. So just going through these problems right here. First off, the probability of an 8. So all this is counting. You've got the picture. How many 8s are there in the deck of cards? Okay, there are 4 8s out of 52 cards. That would reduce to 1 out of 13. But I'm just going to go ahead and use my calculator and round to the 4th decimal place. So 0.0769 is what you should have written down. Anybody got something different we need to talk about before we move on? All right, clubs. How many clubs are there in the deck of cards? There are 13 out of the 52 cards. That reduces to 1 out of 4, which makes sense. There's 1 suit out of 4, and when you make a decimal of that, it's 0.25. Great. Picture cards. How many picture cards are there in my deck of cards? Okay, there are 12. Yes, there are 12 out of the 52, and 12 divided by 52 is going to become 0.2308 when I round appropriately. I'm not seeing any hands, so I'm going to keep moving on. Remember, if you have a question, just get involved. How many cards less than 5 are there in the deck? 16. Yes, remember, less than means we're not counting the 5s. So it's these 16 right here on the end. Remember, ace is 1, so it counts as less than 5. So that is 16 out of 52. 4 goes into both of those if you want to reduce the fraction. I'm just going to go ahead and divide, and I got 0.3077 is my decimal. A red 7. How many red 7s are there in my deck? 2, right? There's the 7 of hearts and the 7 of diamonds. So that's 2 out of the 52. And so that becomes 1 out of 26 if you reduce, or 0.0385. Last but not least, what's the probability that I get a heart that's black? How many black hearts are there? 0. The hearts are red, so that's 0 out of 52. That's an impossible event, and there we go. All right, we've just got a couple more quick problems, and if you have any final questions or thoughts about probability, and then I'm going to let you go free, and maybe you get your homework done as quick as possible and take that quiz, and I also got your test. All right, so these last couple problems just involve looking at area. There's a relationship between probability and area represented. So in this case, the first problem, all of the spaces on the spinner are equal sized. So that makes this a nice relaxing problem. So go ahead and do the probabilities for exercise 6. All right, so the probability of red. So all of these spaces are equal size. They are equally likely outcomes. So how many red spaces are there? 4 out of the 8 spaces. So that means half the time when you spin this spinner, you're going to get a red. How about green? How many green spaces? All right, 3 out of 8. So you're done if you're reducing the fractions, but if not, 3 divided by 8, I think is 0.375, but it's a little early. There we go, 0.375. Yellow, there's 1 out of 8 spaces that are yellow, so that's 0.125. And then not yellow, how many not yellow spaces are there? Yep, 7 out of 8, and that's 0.875. The last problem, I just want to let you know when you have spaces that are not equal sized. So this one, it's fairly straightforward how to resolve, but what you can do, there's, I think, one homework problem that gives you a rectangle and it has different size spaces. And so what you just do is you figure out what the proportion of the actual area is. So like on this one, if I ask you what the probability of green is, how much of this circle is green? Half of it. There's the probability. There's a relationship between the proportion of area and the probability. Another way you can do that on this particular one, and this works sometimes, you can say, oh, but on this one, I could easily make them all the same size. I could take this green space and I could draw a line, right? And now I have all equally sized spaces, so equally likely outcomes, and I can just do what I've been doing. Either way, you're going to get the same result. It's just two different ways of looking at the same problem. So if you would, please finish up these last 4 problems, and then we will be done. All right, so the probability of a red space, there's one red space out of the 4, and that's 0.25. I'm just going to leave that a reduced fraction since it's already reduced. Probability of a green space, we already talked about this one. Either way you look at it, I've got 2 green spaces now that I've divided it up out of the 4, but that just becomes half. Half the circle is green, so the probability of getting green is half, 0.5. Yellow, the probability of yellow is the same as the probability of red because they're the same size spaces. So that's 1 out of 4. And then not yellow. The way I've got it divided up, there are 3 not yellow spaces out of the 4, 0.75, or you can just leave it as 3 over 4.